Hello, everyone, and welcome. Today we're going to be going through Amazon Lookout for Equipment, detecting abnormal equipment behavior by analyzing industrial sensor data. My name is Brent Swidler. I'm the product manager for Lookout for Equipment. So the objective of Amazon Lookout for Equipment is to be able to model the behavior of industrial assets in order to enable predictive maintenance. And I'm going to be going through a lot more in depth on how the service functions and where it's applicable. Just quickly, I want to go through where Lookout for Equipment stands in the AWS ML stack. So we have three layers to the AWS ML stack. There's the infrastructure layer, which includes TensorFlow, PyTorch, MXNet. The middle layer, which is Amazon SageMaker, which allows you to build your own custom models. And then the top layer is managed AI services. There's a variety of different managed AI services, and over here on the right we see the industrial bucket of services, including Panorama, Amazon Monitron, Lookout for Equipment, and Lookout for Vision. So over the next hour or so, I'm going to be going through Lookout for Equipment and the challenges that it addresses in the equipment monitoring and predictive maintenance space. How the service works and some service overview. I'm going to go through a demo of how you can access and use Lookout for Equipment, some common use cases and customer references, and then some getting started resources and where you can access all of the information you need to in order to get started. And then we're going to end with some Q&A. So in the maintenance space, there's been an evolution of maintenance applications over the past number of years where the idea is to be able to move from reactive maintenance, where you're waiting until something breaks in order to fix it, until you can move all the way over to prescriptive maintenance. And that means, first going through reactive and then preventive, which is, what you do with your car, changing its oil every 6 months or however many miles. And so you maintain it on regular intervals. And most of our focus today is going to be on this condition-based / predictive maintenance, which most commonly uses, single variable alarms, some statistical analysis, physics-based modeling methods, and then also what we'll go through in more detail is ML-based approaches. So the objective is to move from reactive all the way to prescriptive. So condition-based and predictive can tell you exactly how your asset's performing now, and then prescriptive in the future is giving you a lot more details into exactly what you should be doing to diagnose a specific issue. And in reality, a lot of different facilities and plants and operations have a mixture of all of these, depending on the criticality of the asset and its operation. It depends on what level of investment warrants moving towards further down this evolutionary chain. What we've seen is a lot of companies are very heavily moving towards condition-based and predictive maintenance and closer to prescriptive. The reason being is because there's a lot of value to be had as we can in savings as you move closer and closer to predictive and prescriptive applications. It's estimated that advancements in maintenance technologies will save an estimated $630 billion across a variety of industries. Some of this is from failure issues. I'm assuming a lot of it is from avoiding downtime. And then there's other, optimizations as well as quality assurance and all of those sorts of things that add up in aggregate to about 630 billion by 2025. Now, because this is such a big number, there's been a lot of investment rolling into equipment health monitoring, which really involves putting a bunch of sensors all over your equipment. Investing in data storage, so all of those sensors take readings all the time and deposit data into what's most often a data historian. Connectivity, which is either remote facilities connectivity or connectivity to the cloud. Analytics, which is what we're going to go into a lot more detail in today. And then also visualizations and the ability to actually give a maintainer some visual aspects to actually help them diagnose and take corrective action. So a lot of investment's been rolling into this space across this entire chain of applications, sensors, data storage, connectivity, analytics, and visualization. But in reality, what that really means is that companies are really drowning in data, trying to figure out how to get value from it. Put a lot of sensors on a lot of equipment. They're all valuable and they're all giving you meaningful information, but at a certain point, it's too much. And from that, it's estimated that only about 5% of the actual data that's being generated from all of these sensors is actually being used. And the reason for this is because there's a lot of information to be parsed through. For any given asset, you can have 20, 30, 50, up to 300. I use tags and sensors interchangeably. You can have a wide variety of different time series sensors coming off of an asset. And so what you're left with is a variety of data sets that look like this that you have to sort of sift through to figure out what is actually a pattern of behavior that you really care about. And how do you spot the problem in when you're not only talking about 300 sensors on a specific asset, but then you're talking about also having 50 assets in a plant and 5 plants, and all as it starts to grow, the complications of the complexity of the problem starts to scale as well. So the current analytic methods do have some limitations in this, but they also do have some positive aspects of how they address some of these problems. The most simplistic and easy to do is single variable analysis, where you say, you can set a threshold saying my temperature is too high or my temperature is too low, and that can start to give you alerts and start to make sense of some of this data. However, you do end up with a situation where you have a lot of alarms. And oftentimes, you're reliant on one specific value to give you a lot of predictive capabilities in what's actually happening in an asset. The next phase in analytics methods is really physics-based modeling, where the engineer, most often who's designed this equipment, can sit down and actually type out or simulate a physical equation to denote how that equipment could operate. And then as we move from single variable to physics-based, the third step here is supervised machine learning applications. And I call out supervised machine learning applications specifically because this is really oftentimes, you'll hear the promise of predictive maintenance. The idea with this type of application is that you would expect that you would say, oh, I have a bunch of failures. Now I can use those as labels and predict exactly what's happening. Here's 50 examples of this asset failing. Can I now use those as labels to predict when that asset's going to fail? And while it sounds logical in this method, it really is not it's not as easy in practice, as this requires a lot of examples of a specific issue. It requires a lot of historical data sets, and it requires a lot of subject matter experts' time to go through and actually make sense of the historical aspects of what has happened in the historical maintenance logs, and put them in a format and structure that can actually be used by ML techniques. And what we've been hearing, across the customers that we work with is that SMEs really feel like a lot of the ML applications are overly consuming of their time and effort. And we have a quote here from one that we've heard from, is that the climb is not worth the view. It just seems like it's way too much upfront effort to get this going. So there are some analytics methods that can help sift through some of this data. They do have some value to them, of course, because they've been, the single variable and physics-based approaches have been being used for a while. But oftentimes there's not a clear way to get like the very direct insights at the speed that's required. And the complication really is that industrial assets are difficult. There's a lot of variability and there's a lot of complexity to this to predictive maintenance applications. So we specifically use unsupervised techniques to try and overcome these problems. But the overall, the problem space can be whittled down to three main issues. And the reason why analytics on industrial equipment is really challenging. One is that every asset is unique. So if you have two pumps right next to each other, even if you're lucky enough that they have the exact same types of tags slash sensors on them, it's often the case that there's rarely two things that operate exactly the same. They might have different maintenance histories, different model numbers, different parts components, and then when you look at, not just pump A next to pump B, but also, a whole plant versus, another plant, maybe a wind farm in Alaska versus a wind farm in Central America, and all of these things start to have so much variability in the way that their data is, that every asset is generally needs to be modeled independently and in a unique fashion. The other issue is that downtime events are rare. So if you heard me say this with the supervised applications, there's very, very rarely a case where you have 50 examples of the exact same failure occurring in some level of history of the asset. Um, and so if downtime events are rare, it's really hard to structure one of those supervised applications because you only really have a small sample size of the types of issues that you're looking for. And lastly, implementation is difficult. So, moving data from on-premise, the sensors to a historian to the cloud to, running inferencing, all of this requires a non-trivial amount of software engineering effort. So here we have every asset is unique, downtime events are rare, and implementation is difficult. So what we've seen is that we need a solution that can do a number of things. We need a solution that can customize to the number of sensors, the unique data, and the operating conditions of each asset, meaning that we build a custom model for each individual asset, regardless of the changing inputs that go from asset A to asset B. The solution that does not require the luxury of having many labeled examples of failure. So I mentioned that we use a lot of unsupervised ML techniques here. This allows us to get around the fact that there's oftentimes a lack of labeled applications and labeled examples of issues that have occurred in the past. We need a solution that can be adjusted over the lifespan of an asset. So another wrinkle in this complication of industrial equipment monitoring is that um, as an asset changes over its lifespan, so does its data set in its definition of behavior, of normal behavior. So, for instance, like I always go to examples with my car. So, a car with 0 miles on it will have a different pattern of behavior than a car with 100,000 miles on it. Both of those data patterns could be considered normal, but they are different, and this pattern of behavior needs to be tracked over its life cycle. We also need a solution that can be scaled across a large number of assets and asset types. So we're not built, here we're not looking at, look out for equipment being something that's like specifically for this type of pump and this type of application. We're building for the ability to ingest data from a wide variety of assets in a number of different industries. And lastly, we feel that this needs to be an automated solution so someone can use it without any ML experience. So we can ask a user a set of questions on their data set, and given their answers to those specific questions, we think we can build an automated ML that Lookout for Equipment does build an automated ML model that can then be used for real-time inferencing. So with those things in mind, we designed Lookout for Equipment. And Lookout for Equipment is an automated machine learning service that uses your sensor data to detect abnormal equipment behavior. So in that first, mess of a bunch of time series that we saw, instead of, now you can take all of that data, bring it all into Lookout for Equipment, and we will use our approach towards modeling the behavior of that equipment, and we can tell you exactly what's normal and when normal behavior is happening in that asset, and alert to any abnormality in the behavior of a specific asset. So over here on the over here on the left, you see all of this mess of data going into Lookout for Equipment. We model out the behavior, and at the output, you'd see, everything is normal, so nothing's wrong. You don't have to do anything. To, hey, we're seeing an abnormality, and most of this is the rank ordered list of exactly what sensor is telling us what's happening here. In a little bit more detail, here is the generalized workflow of how this should work. So we start off with historical data in what's most often either a data lake or in a historian. And then we also have maintenance records. And that those maintenance records, as well as the historical data, and I'll get into what the formats are for this when I go through the demo, are then ingested directly into um, Amazon S3. And look out for equipment set of APIs, just read and write directly from S3. So if you can get your data into S3, you can use Amazon Lookout for equipment. So all you have to do is ingest the historical data into Lookout for equipment, select the sensors that you want to use for a model, click train model, and we automatically train the specific model to that asset. I give you the ability to evaluate the performance with explainability, and then set up that model for real-time inferencing in the cloud. And again, I'm going to go through a demo, so I'm going to show you this entire workflow in how it works inside of the console. So just a little bit of some information from under the hood. Typical ML workflow for an application like this. If we were trying to do this in a manual data science approach, we would have to do a bunch of data cleaning steps, figuring out the right sensors, aligning different timestamps, imputing values. Then you'd actually get to the algorithm selection and the hyperparameters, figuring out how to like create the thresholds and score the models and integrate the historical failure labels, give out the feature rankings. All of this sort of stuff is like step-by-step process. And for anyone who's done a lot of data science work, you could probably understand that every single one of these boxes is still high level, and there's a number of steps underneath that also need to be thought through. So we took it upon ourselves to automate a lot of this away. So here now you can just take your input data, all of those sensors, dump it into Lookout for equipment, and you get a model at the end that can be set up for real-time inferencing. And all of this, all of the complications of all of these steps are just essentially cloud computer time under the hood without user needing to know any of them. So with that, I'm going to jump into a demo. I'm going to go through a demo on an industrial pump. The data set that I'm going to go through is publicly available, and I'll show you where the resources are for you to access and use it. So this specific pump is a pump with 5 different components to it. We have an impeller, a motor, a housing, a volute, and a shaft, and each one of these has 6 specific sensors on it. They're just labeled sensor 1, 2, 3, 4, 5, all the way up until 30. This data set spans from January to November of 2019, and it has 30 sensors on it. The sensors all take readings at a sample of once per minute. And over that 11-month period, there are 10 historical failure events that have occurred. Now, I don't have a class for every single one of those failure events, so we're not saying that this one's cavitation, this one's misalignment, or anything like that. We're just saying here is a behavior of this equipment that was known to be abnormal inside of a given time range. The data formatting looks like this. Let me fill those back in. Okay, so we have our timestamp as the first column in the data set, and every single other column is just a sensor in that data set. So this is the file specifically for the housing. But we have our timestamp in every single sensor. You don't have to format it with 5 sensors, 6 sensors in one file. You can have 1, you can have 3,000. This is just one way to frame the problem. So we're going to ingest this into S3, and then once this is ingested into S3, we'll use Lookout for equipment, and we'll bring it into Lookout for equipment for modeling. So I've now entered into the Lookout for equipment console that can be accessed from just looking for Lookout for equipment in the AWS console. And I've labeled the data set pump example webinar, and I'm going to ingest a new data set into the service. So here, all I have to do is go find that where I've put that CSV file inside of S3, and I'll do that right now. So now inside of S3, I've located all of the folders that have all of those CSV files. So the one that I just showed you for the pump main housing, this is that file that just has all of those sensors affiliated with them in that time series format. And I'm just going to select the folder that contains all of those components inside of them. The last step is just to create a new role and click ingest. So what's happening under the hood here is that we are now taking data from the S3 bucket where those CSV files live and bringing them into Lookout for equipment that can then be used for modeling. So now that my data has been successfully ingested into the service, we'll continue through this workflow. So you see the step 1, create data set. So we've done that. Step 2, we've just ingested the data set. And now step 3, I can create a model. So I'm just going to go click create new model. We'll call this pump webinar model. And now you can see that all of the sensors, from this specific, from that S3 folder are now ingested into the service over here. So I have my volute, my shaft, the pump main housing, the motor, the impeller, and all of this. So if I just wanted to model out a subcomponent of this pump, let's say the volute, I can just click on all of the sensors for the volute. Or if I wanted to model out, any other, subsystem of the pump, I could just select those sensors. In this case, we're just going to select all of them because we want to use all of these sensors for modeling purposes. The next phase is to identify the historical maintenance events as labels. Again, this is optional, so if you don't have historical label events, we can just go ahead without this step. But for those of you that do and want to know how to structure this, the historical label event file just looks like this. So we have column A and column B. Column A is the start time of an abnormal behavior event, and column B is the end time, oftentimes when a failure occurs. The theory here is that inside of this window of time, so this 1-day window of time, there is abnormal behavior prior to a specific failure occurring. Let's say that I forget to change the oil in my engine. Over time, what's going to end up happening is the temperature of my engine is going to be increasing as the amount of lubrication becomes less and less, and my engine becomes less efficient. And so this pattern of behavior of my car engine will start to be abnormal until the car engine fails. So inside of a window of time prior to any equipment failure, there is some behavior pattern, if it's detectable, that should be told here. So here we have our 2 timestamps, our start time and an end time of when an abnormal behavior event occurred in the history of this asset. So all we have to do for Lookout for Equipment is just take that file and point us directly to that file location. So in this case, we just have that file that I just showed had the example labels. It is just this labels1 file. I just have to select the folder, click choose, and create that role. So now we've ingested our industrial data into the service in the form of all of these sensors on these components. I've given the information to those ranges of values, ranges of time at which the equipment operated abnormally. And then I'm just going to select a training time range and a testing time range. So inside of this training range from January 1st, 2019 to August 2019, we're going to use all of the sensor data from all 30 of those sensors to use this to train our model between these times, as well as using the labels from this range over here. Now, keep in mind we're doing this as an unsupervised method, so the labels here are not telling us specific failure modes. Instead, they're telling us that there's just known abnormalities behind the scenes in those ranges. And then we're going to evaluate the model from August 2nd to October 25th. And so what inside of this range, we are just taking the model that was trained at the top range and seeing how it would have performed if it was running on real-time data, evaluating this pump between August and October. The last step here is I could downsample the data set. So in this case, instead of every 1 minute, I want to downsample to 5 minutes. So now I'm just taking readings from this every 5 minutes. And then I can click create. When I click create, all of that automated pipeline that we went through in the PowerPoint, that shows all of the cleaning steps, the algorithm selection, all of that is going to happen under the hood as we train our model. So for the purpose of this demo, I've already done this, so we don't have to wait for this specific model to train. I'm just going to go back to our models here, and you can see the pump demo webinar model. Just center this for everybody. If I wanted to create a new model, I can just do it up here. Now, if I go to pump demo webinar model, I get all of the information for this model. It took 26 minutes to train. It's ready for inferencing. And from a performance perspective, of the labels that were given, we saw abnormal behavior events in 8 of those label ranges, 8 out of the 8 label ranges. And the first anomaly occurs on average 23 hours and 1 minute before the end of the label range. Now, what that really means is that on average, every time that we're detecting an anomaly, we're giving a 23-hour and 1 minute forewarning time for when the asset's going to fail, or however we define that specific label. There are also 5 abnormal behavior events detected outside of the label range. So these could be thought of as false positives. We call them abnormal behavior events because oftentimes there could be something going wrong that might not necessarily be a specific failure. This is the scoring. This is how we score these models. Ideally, we want to make sure that we're alerting to anomalies or issues that are occurring prior to major equipment failures. From the data set, we used January to August to train, and then August to October to test, and the sample rate was 5 minutes. Now visually, it looks like this. We have our gray area where we have the labels of those time ranges, those time intervals. So here's August 8th to August 9th. There was a range of behavior that was known to be abnormal, and so on and so forth through all of these gray areas. And the top portion that's all clickable are the anomalies that are detected from the actual service. So if we play this like a movie over a time range, you can start to see the alerts that you would get, and the alerts are binary output. So it's 0, everything's normal. So that's all this blank space over here. Or 1, the equipment is operating abnormally, and that's what's happening in these brownish red anomaly lines here. Now, again, this is only part of the story. So alerting to a specific issue is nice, but ideally we want to get a lot more granular into exactly what's happening in this asset at this time. So we offer this diagnostic tool to be able to alert to which of the top 15 sensors are telling us that this equipment is currently acting abnormally. So for this specific anomaly, we can see that most of the issues are happening in the volute. So you see this volute sensor 21, 22, 18. This is telling us that the specific issues in this abnormal behavior and whatever failure is about to occur is most likely going to occur inside of the volute. Now, as I go to other failure modes or other anomaly ranges, you can start to see that now the ranking of these features is changing. So now the most prominent features are from the pump main housing, and the pump main housing is a different component of this asset, and this anomaly range is now something that's actually occurring inside of the pump main housing and not necessarily in the volute anymore. And I can continue down each one of these. So this now, as I click on all of these, I'm seeing that most of these issues are now in the shaft of this pump, and not in the volute or the pump main housing. And the idea here is that if you have an asset with upwards of 300 sensors on it, you can ingest all of that data into Lookout for Equipment at once. We can model the behavior or the interactions between all of those sensors together and output results that say, hey, we're seeing some abnormal behavior in this asset, and we're thinking it's because of these 5, 10, 15 specific items or location, specific subcomponents that might be causing it, and give you the exact location and areas where you should be looking. So now that I'm at this step, we've ingested all of the historical data into Lookout for Equipment. We've given ourselves labels in order to train the model that we want. We've trained our model. We've looked at these results. We are very happy with these results because there's a lot of detections inside of the label ranges, and we can make sense of what's actually happening in these sensors. Now I want to put this in for real-time inferencing. So I can just go to schedule inference at the very top, and I'm just going to name my scheduler, and we'll call this, where I have this labeled. So we'll call it pump, I don't know why it keeps changing. We'll call this pump webinar scheduler. And I now have access to the specific S3 location in which I want my real-time data to arrive. So I want my real-time data to show up as real-time data inputs. So I'm just going to select this folder. This is where your historian data moves to S3, or your data lake data, wherever you're having your industrial data being stored in real time. We can push it to this specific folder, and Lookout for Equipment will grab it for inferencing purposes. So I'll choose that. So now what's going to happen is that I'm just going to set a frequency of anywhere between 5 minutes and up to 1 hour. That means that what we're telling Lookout for Equipment now, and what we're scheduling, is let's say if I select 10 minutes, every 10 minutes, Lookout for Equipment will wake up, go and search this S3 bucket for any new data that's arrived from real time, from wherever the data is coming from. We will run that through the model and output the inference results back to the output location that is also user defined. So here I've just defined a bucket location that's real-time data output. And so again, what's happening here is in every 10 minutes, Lookout for Equipment wakes up, searches the S3 bucket for new data, runs it through inferencing, and outputs the result in a JSON file format into this specific bucket. The results will either be binary, so it'll either be 0, everything's normal, or 1, everything's, we're currently seeing an abnormality. And given that we're seeing that abnormality, we will also then rank order all of the features as to what's telling us that this is abnormal. Now, this is where Lookout for Equipment stops. The objective here is to be able to take this output from this S3 location and be able to visualize it inside of a monitoring solution, either custom built or one that's already being used to monitor the equipment that's generating this data. So we've now, in this simple workflow, we've ingested our data into the service. We've given ourselves the label files. We've selected our training times. We've built our model, and we've evaluated our model, and now we have our model running in real time, giving real-time output on the equipment performance for this specific pump. So now that we're done with this pump example, just a little bit more on the use case and application. So ideally, Lookout for Equipment is ideal for process industries. You see 4 buckets here: energy, power utilities, renewables, and process manufacturing. They all have some critical elements in common. Having assets that run continuously, and with limited variability in their operating conditions. So a pump in this example can operate at higher speeds or lower speeds. It can operate with different fluid flows. It could operate with different densities, but in reality, its application is really confined to a number of confined to a number of normal behaviors that can really be defined using ML. Now, on the other side, on the other end of the spectrum, assets like construction equipment such as cranes, maybe like robots or anything like that, have such high amounts of variability in their usage that it's a lot more difficult to actually model out the behavior of a specific asset. I would also bucket things like CNC machines into that more complex area, as those sorts of applications tend to be, if a CNC machine milling part A versus part B is a lot more complex, as each one of those parts might have a different behavior model to it. So while I can't go into a lot of details on all of the use cases for specific customers, we can talk at a high level about the customer applications. Siemens Energy, building a suite of digital services for the energy sector, and looking at using the automated workflows for making it really easy to build and deploy machine learning models across a variety of different asset classes, um, without having to require SMEs to have any data science knowledge. Siemens Energy brings a lot of expertise in both equipment manufacturing as well as um, modeling and understanding their equipment behavior. Leveraging that with the ML output is a great partnership here. One other key customer here is Cepsa Energy. So Cepsa is looking at using Lookout for equipment, bringing machine learning and insights closer to the subject matter experts. So some of the things we've been working on with Cepsa is making sure that we can bring a lot of the ML output as close and very usable for the reliability and maintenance engineers. This will allow them to make a lot more informed decisions and have a lot more relevant and actionable results from the outputs that they're seeing from different models. We also have a great partner network. You'll see a lot of familiar names here, especially Siemens Energy, GE Digital, Hitachi Vantara. We have consulting services with Tensor IoT, Rovisys, and Embassy of Things. We also work closely with our technology partners, so OSI Soft and Seek. And then lastly, for getting started with Amazon Lookout for equipment, always you can go to the aws.amazon.com console and just search for Lookout for equipment. That should land you on the product details page, and all of the information is there. We also have links listed out here where you can get access to the user guide, both in a PowerPoint, not a PowerPoint, a PDF document or an HTML file. We also have free tier usage. So for the first month, you get a certain amount of usage free. That includes 50 gigabytes of free ingestion, 250 hours of free model training, and 168 hours of free inferencing. So that's up to a week of free model inferencing. And then as well, there's a lot of information available on GitHub, and we'll keep populating this with more and more enablement tools. If you go to just github.com /Amazon samples /lookout for equipment demo, everything that I just went through on this demo is there, as well as the data sets and example notebooks on a variety of different applications that make it easy really to get started. And with that, I just want to thank everyone for for your time, and we're going to start a Q&A session now. So feel free to ask any questions that come up. I hope this was helpful, and thank you.